All right, we are at 16.6 combinations of capacitors. We're going to discuss capacitors in parallel and capacitors in series. We're going to start with capacitors in parallel. This is a parallel circuit. If you, well, let me switch to the. I should have started off. Uh, where is new share? And let's go here with the iPad. You can see that really all of this area here, this is all one. This is all one, and the same with the negative. Uh, so if I were to take a voltmeter, and if I were to take, let's just, uh, if I were to put a voltmeter probe here and one here, I would measure a particular voltage, whatever this delta V is. Well, what if I were to move it over here uh, and over here? It would be the same. Over here and over here, it would be the same. I would measure the same voltage because it's really all like one area. So that's um, these are in parallel. So let's go back to um, the uh, PowerPoint. Capacitors in parallel have the same potential difference across them. That's what I was just saying. Wherever you measure, you're going to measure the same potential difference. Um, so here V1, which is the voltage across the C1, and is the same as V2, which is the voltage across C2, which is just the voltage, the delta V across that's coming from the battery. So the equivalent circuit is just the addition of the capacitor C1 and C2. So the total charge is Q1 plus Q2. Well, what is the charge on Q1? Well, it's capacitor 1 times delta V, and Q2 is capacitor 2 times delta V. Well, the equivalent capacitance is Q times the equivalent capacitance times the delta V. Well, what is that? Well, we see C1, C equivalent times delta V is equal to C1 delta V1 plus C2 delta V2. But wait a minute, we just said delta V1, and delta V2 are all the same. Up there in the upper right corner, you see delta V1 equals delta V2 equals delta V. So we can take that out of the equation. We can divide by delta V on both sides, and it all disappears, and you see the C equivalent is equal to C1 plus C2. Let me go back to the iPad, and there's a different way that I want you to look and learn about it. Let's go to the iPad, and let's see what resume share. Okay, so I drew some parallel plate capacitors, and if you recall the definition, the capacitance is equal to epsilon zero times the area divided by the distance. Well, if you look here, this, let's go back to a different color. This distance here is D, and this distance here is D, and this distance here is D. So that it's all the same distance, but notice that you're adding area. This is area 1, area 2, area 3. They're all the same area, so I'm just going to call them A. So if C is equal to epsilon 0 A divided by D, we see that we have epsilon 0 A over D once, plus epsilon 0 A over D twice, plus epsilon 0 A over D a third time. Well, we can, using the distributive property, we can say epsilon 0 times 1 over D times the A plus A plus A. Well, that's epsilon 0 times 3A over D. You can see that the area just adds. And so just like we did in the other, the capacitors in parallel just add. Now, in this case, I used equivalent capacitors, but it would work even if they were of different areas. Okay, let's go back to the PowerPoint and let's see. Okay, let's go back to this. So the C equivalent for a parallel set of capacitors is just C1 plus C2 plus C3. That's a parallel combination. Now let's look at capacitors in series. Now, the voltage is not the same, but I can tell you what is the same. The current, when you initially hook these up, the current is the same, and so the charge that develops across each capacitor is the same. And that's what it says in the sentence. For a series combination of capacitors, the magnitude of the charge must be the same in all plates. So the Q on the first charge is equal to Q on the second charge. So the C equivalent is delta V equals Q over C equivalent. Delta V1 is the Q over C1, and delta V2 is Q over C2. Now the Q is going to be the same because the charge has to be the same on both capacitors. So delta V is equal to delta V1 plus delta V2. So there's this, in the parallel case, we had one voltage across all. Here we have one charge, but different voltage. So that's something to remember. Okay, so delta V equals delta V1 plus delta V2. Delta V is equal to Q over C. So the delta V total is C over Q over C equivalent equals Q over C1 plus Q over C2. So C equivalent is 1 over C equivalent is equal to 1 over C1 plus 1 over C2. Now, trick here, or tripping point. This does not give you C equivalent. This is 1 over C equivalent. So to get C equivalent, you have to take the reciprocal of this. So 1 over C, C equivalent is equal to the sum of the reciprocals, 1 over C1 plus 1 over C2 plus 1 over C3. Now, let's go back to the iPad. And I told you that the one equation, C equals epsilon 0 A over area over D is equal to capacitance is equal to epsilon 0 A over D. Well, here we have A, we have A, we have A. They're all the same area. They're all the same area, but here we've got D, and here, I'm moving my camera. Here we have D, and here we have D. So we've added a little bit of separation with each capacitor. So this C is equal to epsilon 0. It's all the same area. It's all A, but now it's D plus D plus D, and that's E equals epsilon 0 A over 3D. So we've increased the distance between them, and that's why you have to multiply the reciprocals. Now I'm going to show you a little trick. Let's just say you have two capacitors. I like doing it in red. Oops. Let's say you have two capacitors, C1 and C2, and here's your battery. We'll exaggerate the long and the short. Now, 1 over C equivalent is equal to 1 over C1 plus 1 over C2. Now, let's get a common denominator. 1 over C equivalent is equal to C2 over C1 C2 plus C1 over C1 C2. And so 1 over C equivalent is equal to C1 plus C2 over C1 C2, the product. Now let's take the reciprocal of that. C equivalent is equal to C1 C2 over C1 plus C2. Now, this only works when you have a two capacitors in series. It doesn't work. There is no quickie formula for multiple ones. But on a quiz, I'll give you two capacitors, and you can use this formula. C equivalent is equal to C1 C2 divided by C1 plus C2. Now, notice here, this is straight on this other one, or the one that they show you. The one that they show you, 1 over C equivalent is equal to 1 over C1 plus 1 over C2 plus 1 over C3 plus however many you have. You can come up with an answer, but then you have to take the reciprocal to get the actual answer. You can avoid that if there's only two by using this equation here. Okay, let me go back to the PowerPoint, and let's see. Here's a problem-solving strategy for complex capacitor combinations. You combine the capacitors. You redraw your circuit. You repeat the first two steps. Find the charge on the equivalent capacitor. C equals Q over delta V, and then work backward through your diagrams using C equals Q over delta V. C equivalent equals C1 plus C2. Capacitors in parallel and C equivalent of the same delta V. 1 over C equivalent is equal to 1 over C1 plus 1 over C2, or use the little formula that I gave you, C1 plus C2, C1 C2 divided by C1 plus C2. And then capacitors in series and C equivalent, you have the same Q across one. So in parallel, you have the same voltage. In series, you have the same charge. And with that, we're going to stop and we'll go to energy in the capacitor.